Hi, this is problem 2 of EEE 23 problem set. And for this problem, we are given a volume charge density that is a function of the cylindrical coordinate ρ. Okay, so if you're going to imagine this, it's going to look like 4 layers of cylinders, basically. So if you're going to draw the problem, it looks like this. So you have first cylinder from 0 to 2, a second cylinder from 2 to 4, third one from 4 to 5. Sorry, my mistake. It's only actually 3 layers of cylinders, not 4. The fourth layer is there's no cylinder, there are no charges greater than 5. So it's this area outside the 3 layers here. So within the first layer, you have 4 ρ squared. The second layer, you have 18 minus ρ. And the third layer, we have some constant ρ naught. Okay, so that's the volume charge density at each of these layers. If you're going to draw it in 3 dimensions, it's going to look like this. So the first layer is this one. Sorry, that's a bad drawing. I apologize for that. I'm not really good at drawing. Let me try that again. Right. So it looks like this. Okay. So this is the first layer. The second layer looks like this. Oops. And so on and so forth. Right. So basically, you have cylinders within a cylinder within a cylinder. Okay. And we are tasked to solve for the uh, for the electric field everywhere for letter A. So we want to solve for E everywhere. Since our charge density is a function of ρ, we expect the electric field also to be a function of ρ. So when we're talking about E everywhere, we're talking of E as a function of ρ. How do we solve for that? So according to Gauss' law, the closed surface integral of your electric flux density is equal to the charge enclosed. And the charge enclosed can be solved by getting the volumetric integral of your volume charge density. Right. Now, our volume charge density, or our volume basically, is a function of ρ. So the volume of a cylinder is, its volume is equal to pi r, sorry, not r, pi ρ squared times h. Okay, so the differential volume, if the volume is a function of ρ, then the differential volume is 2 pi ρ h. Okay. Therefore, our closed surface integral of d dot ds is equal to 2 pi h times the integral of ρ v times ρ d ρ. I forgot the d ρ here. I apologize for that. When you're getting differential of some value, there should be a differential value also on the other side of the equation. Right. So this is an expression for your closed surface integral. Now, if we are in free space, which is when it's not given, we are assumed to be in free space. So in free space, the electric flux density is related to the electric field intensity by epsilon 0, which is the permittivity of free space. So we have this expression here. Just a note, again, another note, the ds here, okay, the surface defined by ds is related to the cylindrical volume that we use to enclose the charges. So that cylindrical volume, okay, a cylindrical volume of some arbitrary radius, okay, just delete that first. A cylindrical volume of an arbitrary radius could be enclosing the charges like this, the dashed line that you see there. Right, there you go. So that dashed line is a cylinder of height h and a radius, some arbitrary radius rho. Okay, so let me just write that. There you go. And it encloses an amount of charge, and depending on the volume charge density. So from the symmetry of the problem, the electric field will only be going in the rho direction. It only has a rho direction as for its electric field component. Therefore, this integral here, the left-hand side of your equation, will just be equal to epsilon 0 times the integral of E rho, okay, on a surface, and the differential surface is defined by rho d phi times dz. It's equal to 2 pi h is the integral of rho v times rho d rho. Right. Okay. And simplifying this equation on the other side, the cylinder that we use to enclose our Gaussian surface has height h as seen here. So the integral would be, your phi is from 0 to 2 pi, your z is from 0 to h. Okay, this rho is constant with respect to phi and z, so we can just bring that out. We have E rho d phi dz, okay, equal to 2 pi h. It's the integral of rho v rho times d rho. And we have this integral, E rho, is assumed to be constant over the whole surface of your cylinder. Therefore, the result of this integral on the left-hand side equation becomes epsilon naught rho times E rho times 2 pi h. 2 pi h times the integral of rho v times rho d rho. So we cancel this. Okay. In effect, the rho component of the electric field intensity is equal to 1 over epsilon naught times rho, the integral of rho v rho d rho. And you integrate that from 0 to some radius rho. Okay. So that splits our integral into 4 different regions, actually, defined by the bounds of your volume charge density. So for the region 0 to 2, okay, for the region 0 to 2, you have the rho component would be in the integral from 0 to rho, from 0 to 2, rho v is 4 rho squared. So that's 4 rho squared times rho, so that becomes 4 rho cubed times d rho. And you integrate that, you get 1 over epsilon naught rho times rho to the 4th, evaluated from 0 to rho, and the electric field is equal to rho cubed over epsilon 0. This is the electric field from 0 to 2. The next region is from 2 to 4. And from that region, we're going to integrate 1 over epsilon naught times rho, integral from 0 to 2 of your 4 rho cubed d rho, and you add the integral from 2 to rho, okay, of 18 minus rho times rho d rho. And you have this expression for the electric field. So why did we integrate this from 0 to 2 only? It's because if we look at this enclosed surface here on your screen, the Gaussian surface with a radius, a Gaussian cylinder with a radius of rho greater than 2, completely encloses the cylinder within, or the smallest cylinder within your layers of cylinders. So it completely encloses this charge density at the first region and a part of your second charge density. Therefore, our integral will be split into two, like what you see here. So evaluating that, so by integration, you have rho raised to the fourth power, integrated from 0 to 2, plus you have 9 rho squared minus rho cubed over 3, integrated from 2 to rho. Okay? Excuse me. And that results into an electric field of, quite simply, it's equal to negative 52 plus 9 rho squared minus rho cubed over 3 rho epsilon 0. And this is the electric field expression from 2 to 4. Right. So you repeat the same process from 4 to 5. So at 4 to 5, okay, given that rho naught is equal to 10 coulomb per meter cube, the electric field is equal to, 1 over pi epsilon 0, epsilon naught rho rather, and you integrate from 0 to 2 of rho 4 rho cubed d rho, and you integrate from 2 to 4 of 18 minus rho times rho d rho, and finally you integrate from 4 to some value rho, your 10 coulomb per meter cube times rho d rho, and you have an expression for your electric field intensity from 4 to 5. This results to E rho equal to 76 plus 15 rho squared over 3 rho epsilon 0. Okay. And finally, to get the electric field intensity, you just need to repeat all this, but change this one to 5. So in this case, if rho is greater than 5, you're completely enclosing the system by your Gaussian surface. So you're completely enclosing the charge, the whole charge, basically. So completely enclosing that. Let me just copy this first. Okay. There you go. Oops. And here you go. And then we just change this to 5. Alright. And the resulting electric field is equal to 451 over 3 rho epsilon 0. We can now finally write the total electric field in 4 different regions. Okay, so I have rho cube over epsilon 0 a rho hat. So this is now a vector. Okay. Okay, so this is the first region from 0 to 2. Second one is from negative 52 plus 9 rho squared minus rho cubed over 3 rho epsilon 0 a rho hat. And this is from 2 to 4. Finally, you have, no, not finally, second to the last one, 76 plus 15 rho squared over 3 rho epsilon 0 a rho hat. This is from 4 to 5. And finally, you have this is now your electric field function. Okay. Next is letter B. Letter B, what is the electric flux through a surface given? Right, and given a hint, this surface is actually part of a hexagon. So if you draw your system as seen from the top view, the system from the top view looks like this. This is your x-axis, this is your y-axis right here. Your cylindrical system is from 0 to 5. It's the whole circle here. You see here. That may be too big. Let me make it smaller. Nope. Let me try again. Better. There you go. So you have this circle. This is your charge density from 0 to 5. So let this be equal to 5, right? The surface that is given is at x is equal to 6 and is bounded from here to here. It's too long. Let me just fix that. There you go. And is actually part of a hexagon if you extend it. So, oops, just adjust that. There you go. So it's part of a hexagon. We can enclose the system by a hexagonal prism, right? And divide the flux, the total flux, due to symmetry. We can divide the total flux here, let's call it psi e. The same flux is found in this surface here. The same flux is found here. The same flux is found here. Same flux here, here, and here. Wait, this is not a hexagon. I apologize for that. Let me redraw that. Your hexagonal surface looks like this. Alright. Hexagonal surface looks like this. And this is the surface S that we're talking about. Okay. Again, it has a flux psi e due to symmetry. The same flux passes through here, 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 and here, and finally here. And according to Gauss' law, if you have a surface that encloses a charge, then the total flux is equal to the charge enclosed. Right? So the height of your prism, this surface S, the height of that is equal to 6. So we just need to get the total charge enclosed by this hexagonal prism, divide that by 6, and then we get the flux on one side, which is the flux to the surface that we want. So the total charge enclosed is equal to 2 pi times the height, and the integral from 0 to 5 of your charge distribution, rho. Okay? And you can actually solve that from here, and you will get 1804 pi coulomb. And that is equal to 6 times the total flux across the hexagonal prism. And divide that by 6, you get 944.57 coulombs. And this is your answer. Just a note to everyone, it's a common mistake that a lot of you have. The unit for the electric flux, right? Electric flux is in coulombs, as defined by Maxwell. Right? The unit of electric flux is in coulombs, the same as the charge. Right? The unit of Weber is a magnetic flux, which we will talk about in the second long exam. So we won't be using Weber anytime soon. Right? So electric flux, the unit is in coulombs. Right. So last, letter C. What is the value of rho naught such that the electric field intensity at rho greater than 5, okay, the electric field is 0. So to do that, we're going to go back here. Here you go. Right, let me just clean that figure. Right, there you go. Just copy that. And put it here. So to make the electric field outside this system, we want that to be 0. To make that 0, then our Gaussian surface, totally enclosing the charge distribution, the charge enclosed for that surface should be equal to 0. Right? By consequence, since the total charge is 0, then you have 2 pi rho h times the electric field rho component. That will become equal to 0. So we want the charge enclosed by this, which means the total charge inside your distribution, the total charge should be equal to 0. So that means Q equal to 0, which is the 2 pi times h times the integral from 0 to 5 of rho v rho d rho should be equal to 0. So this charge distribution, so if we want that to be equal to 0, then the integral from 0 to 5 of rho v times rho d rho should be equal to 0. And we can split this integral into 3 parts depending on the equation. Since your distribution is piecewise, we have to split this integral into 3 parts. So this 0 must be equal to the integral from 0 to 2 of your 4 rho cubed times rho d rho plus the integral from 2 to 4 of 18 minus rho times rho d rho. And finally, you have the integral from 4 to 5 of rho naught times rho d rho. Okay? There you go. So we can now solve for rho naught here, which is a constant. Since rho naught is a constant, we can solve for its value. Right? So just evaluate this integral, this integral, this integral. These two can be solved using your calculators, numerical integration, and so on and so forth. You'll get rho naught equal to negative 23.4074 coulomb per meter cube. And that's the answer. Okay. So that's the end of problem 2. If you have any questions or comments, do not hesitate to leave a comment in the comment section below. Okay. I trust that you can solve this by yourselves. So you can just input that in a calculator actually. Okay. So thank you for listening. See you next meeting.